Hello everyone. Myself Dr. Rajesh Prasad, currently working as professor in Akgec Engineering College, Ghaziabad. So today I am going to discuss on complexity and asymptotic notations in design and analysis of algorithm. So basically this course is like very popular course in BTech and also very popular in MTech and MCA. So what I'm going to discuss is first one, how to define complexity, and second is how to define asymptotic notations, right? So as we know that complexity of any algorithm is actually amount of time or space, right, required to execute the algorithm. So you know this here. In complexity, we will talk about two type of complexity, time and space. So if you talk about time complexity, that means amount of time required to execute algorithm, right? And if you talk about space complexity, we will talk about amount of space required to execute algorithms, right? So this is generally function of size of n, where n is size of the input. For example, if you talk about Fn is 2n plus 3, so this is linear in time. Okay, so this is actually linear in time. So we will say that, okay, algorithm is running in linear time. So similarly, if you talk about Fn is 100, so it is, this time is actually a constant time. Okay, this 100 is constant time. So this time algorithm is running in constant time. So constant is like every time we are running, getting the same time. For example, see, like if you run in a loop for I is 1, I less than or equal to n, and I plus plus, okay, and let's say if you print something, let's say printing India, okay. So if you print India, this is not like taking different time in every iteration. It's taking the same time in every iteration, okay. So that means its running time will remain the same. So yeah, so this is where we are always getting the constant time, okay. So if you talk about analyzing the algorithm, so generally we are having two type of procedures in algorithms. First one is iterative procedures, where we are using the loop, okay, and the second one we are having recursive procedure, where it is involving recursion. So recursive procedures time is computed in the terms of recurrence relation, right? So we'll discuss it separately. We are going to discuss involving iterative procedure, which is involving the loop. And we know that why we are interested in loop, where there is theory in compiler that 80-20 rule, right? Yeah, 80-20 rule is suggesting that 80% of computer time is spent on the loop and 20% in rest of the work, okay. So there are some rules to understand if you are computing the time of the iterative procedure. First is complexity of data type declaration, which is always going to be 0. This is rule number 1. Why? Because you see, if you might have seen the C program, if you start from main, right, and write down integer I, okay, and let's say another prototype, let's say integer f and integer and float, let's say this is the second one, okay. So in general, you know, if you are running the computer program, compiler will not read this, so their time is always going to be 0. So in fact, compiler is not going there, compiler will not read it. So you may be thinking that, so what is essence if you start writing a program, right, like see here, okay. See, if you go here, like see, if int I and you know, I is 1, okay, and print I, print of I, suppose you are writing print of I here. So you know, in fact, there is concept of symbol table in data structure. So symbol table for each type declaration is maintained in the program. So you know, if it is not reading here, this means that whenever you are coming here, there is a conflict. There is a conflict. So this is not, compiler is not reading over this point, but there will be conflict here because you are writing percentage %d. So if you are not writing integer, it will detect conflict here. What is type of I? That's why we are declaring here. Otherwise, compiler in fact is not reading this. Okay. So complexity of a statement executing constant time is always denoted as 1. So next is complexity of a loop executing n time is going to be n. So let's have one example. So if you see this is iterative procedure. Let's say I is 1. Okay. So this is 1 because it is constant time. So its complexity will be 1. So if you start writing this line, this is a loop. Okay. And this is running n times. So maybe we are wondering that why it is n plus 1. Look at here, it's very simple procedure. Suppose n equal to 5, okay. Suppose n equal to 5. Then I will be how much? I will be 1, okay, then 2, then 3, then 4, then 5. I equal to 5 less than or equal to 5, correct. Whenever I becomes 6, it will fail. It will fail because 6 less than or equal to 5. No. So that means how many time it is running? It is running 5. You took 5, so it is 6. There is another way to compute. You just run an arithmetic progression on this. And you know that nth term of arithmetic progression is an is a plus n minus 1 into common difference. This is also one of the procedure. So if you are running this, let's say 1, 2, it is progression on I, 1, 2, 3 and I, and it will of course fail on I equal to n plus 1. So this is the value actually. It will fail on I equal to n plus 1. So if you apply the arithmetic progression here, a plus I minus 1 into common difference 2 minus 1 is the common difference and this equal to n plus 1. Okay. So here from here 1 plus I minus 1 equal to n plus 1. So I will become n plus 1. This is actually the value. Okay. So I is n plus 1. This is from where we are getting n plus 1. So, and second point, it is the body of the loop. We know that body of a loop is always running 1 less than the loop. Okay. So, its constant time 1 into its body is n plus 1. So, n plus 1 minus 1. So, this become n. So, in total time is computed by adding all of them together. So, which is 2n plus 2 and that can be approximated as big O of n. So this is very simple procedure. So let's have concept of the nesting of the loop. Okay. If you talk about nested loop, you look at here. This is like m plus 1, just like we did the previous question. Okay. And this type of question, you know, this is n plus 1, but remember this is body of the previous loop. Okay. So whenever this is body of the previous loop, so it is previous loop is running m plus 1 time and this will be m plus 1 minus 1. Okay. So this of course is n plus 1 into m. Yes. Okay. So this is the, okay, second thing, if you go to print hello, okay, this is running time of hello is 1. This is body of the this statement. So previous one is n plus 1 minus 1, subtract 1. And now this is body of this statement. Okay. So multiply m plus 1 minus 1. Simple. So if you simplify it, it will be nm, and if you simplify, this is the 1. Okay, let's have an example. If okay, so let us take m equal to 2 and n equal to 3. Okay, no problem. Okay, so this is like if you start run I, okay, and this is j, and let's say this is print. Okay, let's understand whether it is in line with our own understanding or not. I is 1, yes. So j is 1. J is 1. Of course, 1 less than or equal to 3. So j will be 1, 2, 3, and of course it will fail on 4. no problem. But you know, whenever j is 1, 2, 3, it will print hello. It will print hello 3 times. Simple. Okay, this is the first tabulation. Okay, so whenever I is 2, okay, so whenever I become 2, so again j will take 1, 2, 3, 4. And this will also print hello, hello, hello 3 times. And whenever I become 3, it will fail. I become 3, it is not running. So this will not run, this will not run. So let's understand. So that means this guy is clear. 2 plus 1 is clear. That means it is running 3 times. Look at here j. This should be running like this. So n is how much? N is 3. So 3 plus 1 into m. M is 2. So 4 times 2 become 8. Correct. Yes. Look at here. 4 and 4. 8 times. This is in line with our own discussion. Print hello 3 into 2. 3 into 2 means 6. Yes. 6 times hello was printed. So this is correct. That means this answer is correct. So if you want to add overall time, you can add them together to get the total time. M plus 1, then n plus 1 into m, okay, and then nm, yes. So this is actually total time of the algorithm. So this is number 1 procedure, okay. Yeah. Similarly, if you talk about triple loop, you see here, if you just talk about triple loop, so this will like m plus 1, correct, in the same, under the same methodology. And this is n plus 1 into, you know, it is body of the previous loop. So this is m plus 1 minus 1. Okay. Yes. And similarly, if you just like simplify it, m into n plus 1. Okay. Similarly, if you just start here, p plus 1 loop. Okay. And this is body of the previous one. Okay. So body of the previous one is n plus 1 minus 1. Simple. And now this is body of the previous one, and this will be m plus 1 minus 1. So it's very simple, p plus 1 into nm. That is how we are computing. Okay. So if you want to take this guy 1, and this is body of this, so this will be p, and this is body of this is n, and this is body of this is m. So you can compute it to get the overall running time of the algorithm. Okay. This is another example which is very interesting. This is an example of dependent loop. Okay, dependent loop in the sense that run like number of times second loop is running is decided by the first loop, because look at here, I is 1 less than or equal to m. Yes. Now j is depending on I. So if you see here, let's say m is 2. Okay. And if you just run it like m is 2, so definitely you see start from I is 1, yes. So then j is 1 less than or equal to 1, correct. J is like running 2 times, 1 and then 2. It will fail on 2. And print, of course, will print hello only 1 time. This is I equal to 1. Okay. Whenever I is 2, if you talk about I is 2, 2 less than or equal to 2, correct. Then this guy will be running 3 times. Okay. 1, 2 and 3. And this time will be printing only 2 times hello and hello. Simple, 2 times printing only. Whenever I become 3, okay, I become 3 less than or equal to 2, no. Okay, so this is running 1 time, and but j will be only running 5 total. Okay, so let's conclude this, how to compute it. Okay, so first one is not a problem. This is m plus 1. Okay, it's correct, and this guy, you know, is of course depending on I. So you know here, and its running time in terms of I will be I plus 1 minus I plus 1. Okay. Yes. And this I is starting from 1 to m. Okay. So look at here, if you talk about m equal to 2, so I 1, so this become 2, m is 2, so this become 3. So of course this is running 5 times, which is in our own discussion. It is correct, right? Yes. So, and this guy you see here, you know, this guy is 1, okay, and this is also depending on the previous one. So previous one is I plus 1 minus 1, okay. So I is now 1 to I is 1 to m, that means 2, okay. So whenever I is 1, so it will be like 1, and whenever I is 2, it will be 2. We are not interested in going up because this is depending on the previous one. So this is 3, and of course this is the correct answer. So of course this is the running time. So very simple procedure if you are getting the dependent loop, okay. So next category of the loop is logarithmic loop. This is something very interesting, that running time of this type of loop will be given in terms of logarithm. So how to compute, like here, I is 1, I less than or equal to n. Now we are multiplying it. I is 2 times I. Okay. So if you just start a progression on I, so I will be 1, then I will be you see, let's say this is going to be 8. So I will be 2, okay, then I will be 4, okay, and then I will be 8. Up to 8 we are going to have run. Then next one, I equal to like 16, it will fail, this will fail, but of course I will run 5 times, okay. So what is progression? You know, it is geometric progression, and we know that geometric progression, nth term is a r to the power n minus 1, where r is common ratio. So if you are interested in ith term a, first one is this, common ratio is 2, ith term we are interested in, and it is failing whenever it is equal to minimum n plus 1, okay. Yes, it is failing whenever I become n plus 1. So to the power I minus 1 is n plus 1. So I minus 1 equal to log 2 n plus 1. Okay. So this means that I equal to log 2 n plus 1, and of course we are interested in this ceiling function plus 1. Okay, so let's see this, it is in line with our own discussion or not. If n is 8, 8 plus 1 is 9, log 9 base 2 is 3, 3 plus 1 become 4. Yes, you know, see this, log 2, n is 8, 8 plus 1 is 9. So, you know, take ceiling plus 1, log 8 base 2 is 3. So, this is going to be 4. Okay, and 4 plus 1 become 5. So, of course, this is running 5 times. This is correct. And rest rule will remain the same, that body of loop is always running one less than the loop itself. So, this is an example of the logarithmic loop. Okay, yeah. So, another interesting thing is the asymptotic complexity. So, you know, till now we have not discussed asymptotic complexity. So, if you just like follow the mathematics, asymptotic notations, if they follow a particular trend, they will not start another trend. Like, see, if you start a function and if you start increasing, it will always keep increasing. It will not going to decrease. Similarly, if you have a function, this will start decreasing. So, it is always going to decrease. It is not going to increase and decrease. Like you see, if you start like this type of function, sinusoidal wave or cosinusoidal wave, they are not going to be categorized as asymptote. So generally, you know, in the algorithm, if we start running if we start running an algorithm and time start increasing based on the value of n. If size is increasing, value will increase, right? So that means we are interested in asymptotic notations. Okay, so there are 5 types of asymptotic notations: theta, big O, omega, small o, and small omega, right? Yes. So if we start like understanding theta notation, we know that if we have two function fn and gn, okay, so we can say that fn is theta of gn, okay, if and only if fn lies between this. So you see fn is lying between gn, so fn less than or equal to c2 gn and c1 gn. That means this is how we are defining the theta notations, right? fn lies between this one, and for like n should be greater than or equal to n naught. It's very basic concept, right? And C1 and C2 you can decide by yourself. Yes. And like here, if you see, like example is very simple, like you can take this 10n square minus 3n. This can be approximated as theta n square. Similarly, if you can take like fn is 2n plus 3, okay. So if you want to approximate to theta notation, so this is 2n plus 3 less than or equal to c2 gn, and take the highest dominating factor. So this is n, and take this also highest dominating factor is n. Okay, and n should be greater than or equal to a particular n naught. So you have to satisfy both this upper identity and lower identity, right? So in that situation you can choose C1 and C2. So if it is working like this, so then this will also work. Okay, so in that situation, whatever constant this is having, you just increase by 1, so it is going to be 3n. So if any n naught you are choosing, this should work for both the values. Okay, yeah. So another notation is big O notation. Is very simple, that if you talk about fn and big O of gn, okay, so fn should be less than or equal to c into gn. So you know c and n is greater than or equal to n naught. You can define c and n naught. If it is working, that means fn will be treated as big O notation. Another notation is like omega notation. So fn is omega of gn, means that fn should be greater than or equal to cgn, okay, and n greater than or n equal to n naught, and c is a constant. So you might have noticed that this is measuring the lower bound, and big O notation is measuring the upper bound, and theta notation is measuring the tight bound. Okay, so in general, like asymptotic notations, they are very simple to understand. Another notation is small o notation. We say that fn and gn, they are little o of this gn if and only if limit n tends to infinity, fn by gn is equal to 0. In other words, you just remove the equality from this notation, don't write less than or equal to, you will get the little o notation. Similarly here, we say that fn is omega notation little o if limit n tends to infinity, fn by gn equal to infinity. So they are very like, this is the limit rule, and we can go through this limit rule. It is very simple, and this big O, omega notation and theta, they follow the properties, right? So they are reflexive and they are like this is the transitive notation. Theta is transitive and big O and fn is also transitive. Okay, so this they follow the reflexive and transitive property, but they don't follow the symmetry property, especially big O and omega. Only theta follow the symmetric property. These are the references. Okay, you can follow. Thank you.